Welcome to lecture series on Unit 6, that is combined loading. This Unit 6 is included in the SE 2019 course syllabus. For SE 2024 course, this part is included in the Unit 5 along with the principal stresses. So Unit 6 is combined loading. So we'll try to understand various terms in it. First of all, direct load. This is the column, rectangular column, and it is subjected to a compressive load P, and this load acts at the CJ of this column. So this load is considered as a direct axial load. So direct axial stress developed in the column is direct stress is equal to direct load divided by cross-sectional area. If it is a rectangular cross-sectional area, cross-sectional area is B into T. So direct axial stress is denoted as sigma naught, and that is equal to P by A, where P is the compressive load divided by A is the cross-sectional area of the column or member. Now, next type of load that is coming is on the column is a eccentric load. So second figure shows the eccentric load. So the load magnitude is same, that is a compressive load P, but it is not acting at the CJ of this column. So it is offset by a certain distance, and that distance is called as eccentricity. So this load is called as an eccentric load. So for eccentric load, we can see in the figure, this first figure, this is axis of the column, and load is acting at a distance E, that is called as eccentricity about the axis, eccentricity of the load P about from the axis. So this load is called as a eccentric load. So eccentric load is replaced by two loads. First effect of eccentric load, it acts as a direct load. So in the first figure, this column is considered as it is subjected to direct axial load, compressive load, that is P. And here we are considering section 1, 2 at anywhere in the column. So at this section, there is a direct stress induced in the column, and this direct stress is uniform, and its magnitude is sigma naught. Sigma naught is equal to direct axial load divided by cross-sectional area. So this is a sigma naught is the direct axial stress, and plus there is another effect of this load, that is a bending effect. So this load is acting at a offset distance, that is E, which is called as eccentricity. So from the about the axis, this load into distance, it creates a moment. And this moment direction is shown here. The moment is of magnitude m, and that is nothing but equal to load P into its distance from the axis, that is eccentricity. So m is equal to P into E. So this is a bending moment. So under the action of bending moment, we know bending stresses are developed in the column. So bending stresses, its magnitude, bending stress, its magnitude is given by, you can see, bending stress का magnitude कितना होता है? Bending stress is given by m by z, where m is nothing but the bending moment acting on the column. Here in this case, bending moment is nothing but load into distance, that is P into E, divided by sigma B is equal to m divided by z. M is the bending moment acting on the column about its axis. So that is of magnitude P into E, divided by section modulus of the cross section of the column. So Z is the section modulus. So sigma B is equal to m upon Z. This is the bending stress formula, or bending stress is also given by m upon I into Y. I upon Y max is nothing but Z, section modulus Z. So Z is the section modulus, and its unit is mm cube. We have seen or discussed these problems in our unit 3A part, bending stresses in B. So Z is calculated by Ixx upon Y max, Ixx upon Y max. So this is Zxx. Similarly, Zyy is Iyy upon Y max. So Z is nothing but the section modulus. So we know bending stress, its magnitude is bending stress is directly proportional to Y, and Y is maximum at the outer surface of the column. So at the centroidal axis, the bending stress is 0 because Y is 0, and as we go towards the outer surface, Y get increased, therefore bending stress magnitude is maximum at the outer surface. So here in this case, the bending stress distribution is a linear straight line distribution, and bending stress is maximum at the outer surface, right surface and left surface. Bending stress distribution is a linear distribution. Its intensity is maximum. Bending stress is maximum at the outer surface, right, at the right surface, and at the left surface the bending stress magnitude is maximum. Column ऐसे बेंड हो रहा है, मतलब this half portion of the column is subjected to compressive stress. So यहाँ से एक्सिस से ये राइट का पार्ट है, ये बेंडिंग स्ट्रेस ऑफ compressive नेचर है, और लेफ्ट का पोर्शन जो है वो बेंडिंग स्ट्रेस ऑफ टेंसाइल नेचर. सो दिस इज सिग्मा बीटी एंड दिस इज सिग्मा बीसी. सो इफेक्ट ऑफ एक्सेंट्रिक लोड on the column, there are two effects. One, it produces a direct stress of magnitude sigma naught, and also it produces a bending stress of magnitude sigma b. Bending stress of magnitude sigma b. और bending stress कैसे कैलकुलेट करते हैं? तो m by z, right? And m is nothing but p into e upon section modulus z. So the combined maximum stress in the column under eccentric load is calculated as sigma max is equal to sigma naught, that is direct axial stress plus bending stress. Sigma max is equal to direct axial stress is P by A plus bending stress is given by M by Z. And this maximum stress is of a compressive nature, because we can clearly see columns are always subjected to compressive load. Column है तो column पे compressive load आता है. So maximum stress developed in the column is of a compressive nature, right? And unit is Newton per mm square. So this is about combined maximum stress. Now minimum stress, combined minimum stress, sigma min is equal to sigma naught, that is axial stress, direct axial stress minus sigma b, where sigma minimum is equal to axial stress is P by A minus M by Z. This is also compressive. Both are compressive in nature. So this is about eccentric load about only one axis. ये eccentric load about only one axis है, एक axis को ही eccentric है. तो दूसरा केस हमारा दूसरा केस ये है, इन केस ऑफ सिमेट्रिकल कॉलम विथ एक्सेंट्रिक लोड अबाउट टू एक्सिस. समझो यहाँ फिगर में कॉलम देखेंगे, द कॉलम ऑफ रेक्टेंगुलर क्रॉस सेक्शन whose width is b and depth is d, and this is a x axis, x axis, and this is a y axis. So this is a symmetrical column about x axis and about y axis. Now load position is here. This is the point of application of the load P, that is compressive load P. So this load P is offset from x-axis by distance which is called as EY. हमने इसको EY क्यों बोला? कि it is parallel to y-axis. That's why EY. So offset distance of the load P from the x-axis is nothing but EY. Eccentricity of the load P about x-axis is nothing but EY. And what is EX? EX is nothing but eccentricity of the load P from the y-axis. And it is denoted as EX because it is a horizontal distance. EX क्यों denote किया हमने? Because it is a horizontal distance of load P from the y-axis. और ये distance EY क्यों बोला हमने? Because it is a vertical distance of the load P from the x-axis. That's why it is EY. So EX and EY are the eccentricity of the load P from the x axis and y axis respectively. तो ये हमें ठीक से समझना है. तो एक्सेंट्रिक लोड का दो इफेक्ट होते हैं. एक्सेंट्रिक लोड प्रोड्यूसेस अ डायरेक्ट कंप्रेसिव स्ट्रेस, दैट इज सिग्मा नॉट इज इक्वल टू P by A, वेयर P इज द कंप्रेसिव लोड एंड A इज द क्रॉस सेक्शनल एरिया ऑफ द कॉलम. अगर कॉलम रेक्टेंगुलर क्रॉस सेक्शन का है तो B इंटू D. कॉलम अगर स्क्वायर क्रॉस सेक्शन का है तो B स्क्वायर और D स्क्वायर. अगर सर्कुलर क्रॉस सेक्शन का है तो pi by 4 D स्क्वायर. राइट? इन दिस वे वी हैव टू फर्स्ट कैलकुलेट डायरेक्ट कंप्रेसिव स्ट्रेस डेवलप इन द कॉलम. और दूसरा स्ट्रेस जो डेवलप होता है वो बेंडिंग स्ट्रेस है. So sigma b is equal to m by z. तो दूसरा बेंडिंग स्ट्रेस है. Therefore, the stress at the four corners, ये प्रॉब्लम आता है. Find out the resultant stress at the four corners, that is A, B, C, D of the column. So resultant stress at the corners of this column is calculated by this generalized formula. Sigma is the resultant stress at the corners is equal to direct compressive stress plus or minus sigma bx plus or minus sigma by. What is sigma bx bending stress about x-axis? What is sigma by bending stress about y-axis? So यहाँ प्लस माइनस लिखा है हमने क्योंकि ये जनरलाइज इक्वेशन है. कुछ कॉर्नर्स पे सिग्मा बी एक्स प्लस रहेगा, कुछ कॉर्नर्स पे माइनस रहेगा, कुछ सिमिलरली सिग्मा बी वाई कुछ कॉर्नर्स पे प्लस रहेगा और कुछ कॉर्नर्स पे माइनस रहेगा. वो हम प्रॉब्लम में डिस्कस करेंगे. इसके ऊपर एक हम प्रॉब्लम लेने वाले, वो प्रॉब्लम इंपॉर्टेंट है एग्जाम पॉइंट ऑफ व्यू. सो सिग्मा इज इक्वल टू P by A, दैट इज डायरेक्ट कॉम्प्रेसिव स्ट्रेस, प्लस और माइनस सिग्मा बी एक्स कैसे कैलकुलेट करेंगे हम? mxx बेंडिंग मोमेंट अबाउट x एक्सिस अपॉन सेक्शन मॉडुलस zxx. So mxx upon zxx gives us the sigma bx, and similarly sigma by is myy upon zyy. और दोनों को प्लस माइनस लिखा है इसलिए कि हर एक कॉर्नर्स पे वो कब प्लस लेना है कब माइनस लेना है वो हम डिस्कस करेंगे. प्रॉब्लम डिस्कस करते वक्त डिस्कस करेंगे. तो इसी फॉर्मूले से इफ द सिमेट्रिकल कॉलम विथ एक्सेंट्रिक लोड अबाउट 2 एक्सिस है तो ये फॉर्मूला हमें यूज करना है. सिग्मा इज इक्वल टू पी सिग्मा नॉट प्लस और माइनस सिग्मा बी एक्स प्लस और माइनस सिग्मा बी वाई एंड सिग्मा इज इक्वल टू पी बाई ए प्लस और माइनस एम एक्स एक्स अपॉन जेड एक्स एक्स प्लस और माइनस एम वाई वाई अपॉन जेड वाई वाई. सो नेक्स्ट कंबाइंड लोडिंग इस यूनिट में नेक्स्ट प्रॉब्लम आता है शाफ्ट सब्जेक्टेड टू कंबाइंड बेंडिंग मोमेंट एंड ट्विस्टिंग मोमेंट. ये प्रॉब्लम आता है एग्जाम में. इट कम्स अंडर कंबाइंड लोडिंग केस. So, circular shaft subjected to combined bending moment M and twisting moment or torque T. So, stresses developed in the shaft is it is a combined effect of bending stress that is sigma p and torsional shear stress that is tau. Under the action of the vertical load, the shaft gets bent. So, bending stress is developed in the shaft, and while transmitting torque, it is subjected to torsional shear stress. So, torsional shear stress tau is developed in the shaft cross section. The torque that is applied on the shaft from the resultant effect of bending moment M and twisting moment T is called as the equivalent twisting moment or equivalent torque. So equivalent torque acting on a shaft is calculated by this formula, that is root of M square plus T square, where M is nothing but the bending moment acting on a shaft, T is nothing but the torque transmitted by the shaft. So equivalent torque, it is equivalent torque. So equivalent torque is acting on the shaft when there is a combined effect of bending moment as well as twisting moment, that is T. Right? So bending stress under the action of the vertical bending load acting on a shaft. Shaft is transmitting power, at the same time vertical bending load is coming on it. So bending stress is developed in the shaft and it is calculated by this formula M upon I into Y, where M is nothing but the maximum bending moment acting on a shaft, I is nothing but moment of inertia of the cross section of the shaft. सर्कुलर क्रॉस सेक्शन का Ix और Yy इक्वल होता है एंड दैट इज इक्वल टू पाई बाय 64 d raised to 4 where d is the diameter of the shaft multiplied by y is nothing but distance of the outer surface of the shaft from the neutral axis. So y is d by 2, y is nothing but d by 2 radius, d by 2 is nothing but radius. So distance of the outer surface of the shaft from the neutral axis is nothing but d by 2. So bending stress is calculated, its magnitude is calculated by this formula M upon I into Y. Torsional shear stress, we have the equation T by J is equal to tau by R. This is a torsion equation based on a shear stress. So from that, torsional shear stress is calculated as tau is equal to T by J into R, where T is nothing but the torque acting on the shaft and its unit is Newton into mm. J is the polar moment of inertia of the cross section of the shaft. Shaft is always a circular cross section. तो J क्या होता है? J is the polar moment of inertia. Polar moment of inertia is also denoted as IZZ. IZZ is equal to Ixx plus Iyy. So polar moment of inertia is double that of Ixx or Iyy. Ixx और Iyy same होता है circular shaft का. So polar moment of inertia is twice of Ixx or twice of Iyy. Therefore polar moment of inertia is equal to 2 into pi by 64 d raised to 4. Therefore J is equal to pi by 32 into d raised to 4. Polar moment of inertia circular cross section of shaft का कितना होता है? Always it is pi by 32 into d raised to 4, where d is the diameter of the shaft. R is nothing but radius of the shaft. अगर diameter पता है तो radius कितना होता है? हाफ होता है, तो radius R is in mm. So torsional shear stress is calculated by this formula T by J into R, where T is the torque, J is the polar moment of inertia, that is pi by 32 d raised to 4 multiplied by d by 2 multiplied by radius R is nothing but d by 2. So this is we can say equation 3. Now in such shaft, when shaft is subjected to combined bending moment and twisting moment, then in such shaft there is a maximum and minimum principal stresses are developed. So maximum principal stress is calculated as sigma n1 is equal to sigma b by 2, where sigma b is the bending stress, sigma b by 2 plus root of sigma b by 2 square plus tau square, where sigma b is the bending stress and tau is the torsional shear stress. तो ये मैक्सिमम प्रिंसिपल स्ट्रेस है, मैक्सिमम प्रिंसिपल स्ट्रेस. नाउ मिनिमम प्रिंसिपल स्ट्रेस डेवलप इन द शाफ्ट व्हिच इज सब्जेक्टेड टू कंबाइंड लोडिंग. सिग्मा n2 इज इक्वल टू सिग्मा b by 2, ये माइनस साइन है, into root of sigma b by 2 square plus tau square. So equation 4 and 5 gives us the value of maximum and minimum principal stress developed in the shaft cross section. This maximum stress is also denoted as sigma max, or it is also denoted as a sigma n1. Sigma max and sigma n1 is one and the same. Maximum principal stress, sigma max, or it is also denoted as a sigma n1. So sigma n1 is also denoted as denoted by this formula, can be calculated by this formula. Sigma n1 is equal to 1 upon Zp into m plus root of m square plus t square. तो यहाँ पे एक Zp टर्म आया. What is Zp? Zp is nothing but J by R. It is a ratio of polar moment of inertia of the shaft cross section upon radius of the shaft. This J by R ratio is called as a polar section modulus. Polar section modulus. Polar section modulus is a ratio of polar moment of inertia of the shaft cross section divided by radius R. Radius R. तो ये हमें ध्यान में रखना है. Zp is equal to J by R. और J कितना होता है? Zp is equal to J कितना होता है? Twice of Ixx और twice of Iyy upon radius. Ixx और Iyy सर्कुलर क्रॉस सेक्शन के लिए सेम होता है. Pi by 64 into t raised to 4. राइट. तो Zp हमें इस फॉर्मूले से कैलकुलेट करना है. J by R. J का फॉर्मूला है Pi by 32 t raised to 4. R का फॉर्मूला है R is equal to D by 2. तो मैक्सिमम प्रिंसिपल स्ट्रेस हम इस फॉर्मूले से भी कैलकुलेट कर सकते हैं. 1 upon Zp into m plus root of m square plus t square. What is m? Bending moment acting on a shaft. What is t? Torque acting on the shaft or torque transmitted by the shaft. तो ये मैक्सिमम प्रिंसिपल स्ट्रेस का इन टर्म्स ऑफ पोलर सेक्शन मॉडुलस और बेंडिंग मोमेंट m and t के फॉर्म में ये फॉर्मूला है. दूसरा है मिनिमम प्रिंसिपल स्ट्रेस 1 upon Zp into m minus root of m square plus t square. राइट. मैक्सिमम के लिए ये साइन प्लस है, ये साइन प्लस है. मिनिमम के लिए ये साइन माइनस है. राइट. Zp बोलना नहीं है. Zp इज व्हाट? J by R. राइट. J by R. तो यहां पे इक्विवेलेंट बेंडिंग मोमेंट शाफ्ट पे कितना है वो कैसे कैलकुलेट करेंगे? m इक्विवेलेंट इज इक्वल टू 1 by J. J इज द पोलर मोमेंट ऑफ इनर्शिया into m plus root of m square plus t square. This is equation 8 which is used for calculation of equivalent bending moment on the acting on the shaft. तो आगे प्रॉब्लम में ये फॉर्मूलेज आने वाले हैं, इसलिए ये फॉर्मूलेज हमें समझना है और ध्यान में रखना है. राइट. तो इक्विवेलेंट बेंडिंग मोमेंट इस फॉर्मूले से हमें कैलकुलेट करना है. नेक्स्ट हमें कैलकुलेट करना है मैक्सिमम शियर स्ट्रेस. मैक्सिमम शियर स्ट्रेस इज कैलकुलेटेड एज सिग्मा मैक्स माइनस सिग्मा मिनिमम डिवाइडेड बाय 2. सिग्मा मैक्स और सिग्मा मिनिमम हमने कैलकुलेट कर लिया. दोनों का डिफरेंस लेके हाफ करना है उसका. दैट इज इक्वल टू रूट ऑफ m स्क्वायर प्लस t स्क्वायर अपॉन Zp. Zp is nothing but J by R, that is polar section modulus. M and T are the bending moment and torque acting on the shaft. Then last is equivalent torque. Equivalent torque, we have the torque equation. Equivalent torque TE upon J. T by J is equal to tau by R. So TE is equivalent torque upon J, that is polar moment of inertia, is equal to tau max by R. Therefore, equivalent torque TE is equal to tau max into J by R. Tau max कितना है? ये यहाँ पे root of m square plus t square upon Zp. Root of m square plus t square upon Zp multiplied by J by R. J by R multiplied by J by R. J by R is nothing but Zp. J by R is nothing but equal to Zp. तो यहाँ पे पोलर सेक्शन मॉडुलस ये कैंसिल आउट हो जाएंगे. इक्विवेलेंट टॉर्क का फॉर्मूला आया. इक्विवेलेंट टॉर्क इज इक्वल टू रूट ऑफ m स्क्वायर प्लस t स्क्वायर. और इक्विवेलेंट टॉर्क का यूनिट क्या होता है? इक्विवेलेंट टॉर्क का यूनिट होता है न्यूटन इंटू mm. टॉर्क का जो यूनिट है वही इक्विवेलेंट टॉर्क का यूनिट है. तो ये फॉर्मूलेज हमें ध्यान में रखने और इसके बेसिस पे हम नेक्स्ट लेक्चर में इसके ऊपर एक प्रॉब्लम हम सॉल्व करेंगे. थैंक यू वेरी मच.